In the first video, we mentioned the fact that ionic compounds dissociate in water. The word dissociate meant to separate into charged ions. Well, if you do have little charged ions floating around in solution, those moving charges will conduct an electric current, and we call the solution an electrolyte. So this sodium chloride is a good example. I think it's the one that we mentioned in the last video, that in solution, the sodium and the chlorine will separate or dissociate from the solid crystal, and you'll have these negatively charged chlorine ions and these positively charged sodium ions. And the only thing that's kind of left off in this picture is the water molecules that are surrounding each ion. But in general, we've got moving charges, and this solution should conduct electricity relatively well. We call this a strong electrolyte. A strong electrolyte is something that completely ionizes. And by completely ionize, we mean 100%. So in a solution of sodium chloride, there are no neutral molecules. If I had 100 sodium chloride molecules in water, every one would split to form ions. So if I were kind of writing this as I could say like as an equation, I could say something like sodium chloride dissociates into sodium ions and chlorine ions. And if I had 100 molecules of sodium chloride, they would dissociate to form 100 sodium ions and 100 chlorine ions. No neutral molecules left in the beaker. Everybody splits. Everybody's charged, which is why we conduct a good electric current. Now, we usually don't put the water as part of the equation because water kind of stays H2O molecules. The water molecules just surround the individual ions, but they don't change in any way. They're still H2O. So we often leave water out of the dissociation equation because water's not really changing in any way. It's the sodium chloride that splits into sodium and chlorine ions. Other good examples of strong electrolytes. So ionic compounds that dissolve well in water, those are strong electrolytes. Strong acids. And that's what we mean by saying a strong acid. An acid is a solution that has hydrogen ions present. A strong acid will completely ionize or completely dissociate to form those hydrogen ions. So like HCl, hydrochloric acid, is a strong acid. It's an acid because one of the ions formed is hydrogen, and it's considered strong because it dissociates 100%. If you're looking at an equation and you see that original compound, and then you see the arrow immediately pointing to ions, that's trying to show that it's a strong acid. It dissociates 100% to form ions. So let's write that in here. 100% dissociation. That's what we mean by saying strong. And the acid part means that one of the ions is hydrogen. So again, here's kind of what I'm thinking in my head when I picture a solution of hydrochloric acid with the water molecules left out because they're not really changing in any way. I picture positive hydrogen and negative chlorine ions just swimming around in the water. These are all other good examples of strong acids. Nitric acid, sulfuric acid, only the first hydrogen. And that's another thing that we'll talk about when we get into acids and bases. Sulfuric acid has 2 possible hydrogen ions, but only the first dissociates 100%. So we usually write sulfuric acid kind of like this, 1 hydrogen, and then we'll list this hydrogen sulfate ion. Those are all good examples of strong acids. Another good example of a strong electrolyte, strong bases. Bases form hydroxide. So if I look at a solution and I see hydroxide ions present, I can tell you right away that it's a base. A strong base will completely ionize to form hydroxide. So again, in this beaker, there are no neutral sodium hydroxide molecules. Everybody splits. That's why it's considered strong. The base part is because one of the ions is hydroxide. Any soluble hydroxide, any hydroxide that dissolves well, is usually considered a strong base. So like sodium hydroxide is probably the most common strong base that we'll use. Again, something that dissociates 100%. Now, there are some weak electrolytes. And again, we mentioned that a weak electrolyte, or something that's maybe only partially soluble, may form some ions, but not 100%. So here's some good examples of weak electrolytes. Weak acids. The word acid means that hydrogen is formed. Okay, so, maybe I see something like this, where there's hydrogen ions formed. The other option is this. H3O plus is also the sign of an acidic solution. We call this the hydronium ion. Now, you might remember this. It's probably like the last thing you did in first year chem, getting into acids and bases. The hydronium ion is the sign of an acidic solution. Here's kind of what happens. Obviously, there's water molecules present. They often leave them out. In this picture here, there's no water molecules shown, but they're present. And obviously, water molecules have a partial positive and a partial negative. So you get something that kind of looks like this. H2O molecules are swimming around, and then all of a sudden, the solution starts getting a buildup of hydrogen ions from the acid, whatever the original acid might be. Well, on the water molecule, the oxygen end was partially negative. So you get a little attraction here. That negative oxygen end of the water molecule is attracted to those hydrogen ions that are being formed in the solution. So you can write acidic equations either way. Usually strong acids are written like this, where you'll just see the acid, and then it completely breaks down into the hydrogen ion, and then what other ion is formed, whatever the negative ion is. Often weak acids are written with water on the reactant side. And that hydrogen ion that's removed from the original acid is attracted to the oxygen end of the water molecule. Opposites attract. So on the product side, they'll often write it as H3O plus, the hydronium ion. And then we've got this negative acetate ion. Either is the sign of an acid. Whether the hydrogen is free floating or whether the hydrogen is attracted to the water molecule. Either way, I'm showing that there's extra hydrogen in the solution. Now, the trick with a weak acid is that this whole dissociation, this losing your hydrogen thing, it might only happen 1 out of 100 molecules. That's the big difference between strong and weak. In a strong acid, everybody splits. In a weak acid, maybe 1 out of 100. And that's what they're trying to show in this picture. Now, they don't have 100 molecules here, but I've got 1 molecule that's split to form the little baby hydrogen ion, and then this would be the acetate ion. But most of the other molecules are neutral. So we can make ourselves a little note. This will be mostly neutral molecules. And I'll even write it as acetic acid, H3O2 molecules. Only a few will dissociate. And we still call the solution acidic because there are some extra hydrogen ions. But it's a weak acid because there's not a lot. It's not 100% dissociation to form hydrogen ions. Just a few molecules will give up their hydrogen. So we also call that a weak electrolyte then. If we don't have a lot of charged ions, we're not going to conduct a lot of current. Will this conduct electricity? Sure. But nothing like hydrochloric acid or a strong acid. Another example. I bet you can guess it. Weak base. Weak bases are weak electrolytes. And again, we're going to spend an entire chapter second semester on acids and bases. We just kind of want to get some of this vocab down so that when we get there later on and we go into more detail with, like, why is this weak or why is this strong? The general term strong and weak makes sense to us. Strong meaning it dissociates 100%. Weak meaning we might dissociate 1 out of 100 molecules. A base should form hydroxide. So at this point in the game, all I need to do is look at this equation and be like, yep, that's a base. It's actually ammonia. NH3 is ammonia, and it's a weak base. It's a base because one of the ions formed is hydroxide, but it's a weak base because this doesn't happen very often. Maybe only 1 out of 100 molecules will actually form these ions. And of the 2 ions, ammonium and hydroxide, one of them is the sign of the base, the hydroxide ion. And now one of the things that we'll kind of talk about is that in this case, you might remember the Lewis structure for ammonia. It's got a nitrogen with 5 valence electrons. 2 are paired, 3 are single. And then we've got the 3 little hydrogen, each having 1 valence electron. Bloop. They're cute. And now that nitrogen has a lone electron pair sitting up on top. Okay, that's negative, obviously. And the nitrogen has a pretty high electronegativity. So the electrons in these bonds are kind of drawn toward the nitrogen. So our friend nitrogen is partially negative. And then the little hydrogens build up a partial positive. And don't freak out. We're going to spend plenty of time on bonding around Christmas. But we want to kind of understand why we're forming hydroxide. In this case, the hydrogen from the water molecule, one of the hydrogens from a water molecule, gets attracted to that negative nitrogen. So if I drew a water molecule, and maybe we'll go something kind of like this. I think this is how I drew it earlier. The oxygen has its 6 valence electrons. 4 are paired and the 2 are single. So here's my water molecule. That negative nitrogen is attracted to little hydrogens because, again, in the water molecule, we have something similar going on. The oxygen's negative. The hydrogens are positive. So one of these little hydrogens gets attracted to the negative nitrogen. So on the product side, we form NH4 plus, the ammonium ion, and then the other ion is hydroxide. All we're left with here is the OH group, and it will be negative. It's missing its positive hydrogen. So for now, all I have to do is be able to look at that equation and say, yeah, that's a base. It's got hydroxide formed. It's a weak base because only 1 out of 100 molecules might actually do this. And if I look at the picture, it confirms that. Oh yeah, here's that ammonium, here's that hydroxide, but it's mostly neutral ammonia molecules. Another sign of a weak solution, when you look at the equation, a weak acid or base will often have water written in the equation. because the water kind of changes a little bit. Water is the source of the hydrogen, so water changes from H2O to just OH. So they'll put the water in an equation if water does change, and that's what happens in these weak bases, or even a weak acid. If I look back at some of these weak acids, now the water started as H2O, but if water picks up a hydrogen, it does kind of change. So if you see water in the equation, that's another good sign that the solution is a weak acid or a weak base. Or in general, we could call it a weak electrolyte. So the main difference, let's say I use these bases. Sodium hydroxide, strong electrolyte. Strong electrolyte, or we can even be more specific and say a strong base, because one of the ions formed is hydroxide. It exists as ions, as dissociated ions, little charged particles. Conducts good electricity, which is why not only we can call it a strong base, but we can call it a strong electrolyte. Ammonia is a weak base. Does it form hydroxide? Yeah, there's a few, but not a lot. It's mostly neutral molecules. Main difference between strong and weak acid or base. Another option would be a non-electrolyte. Non-electrolyte is a solution that doesn't form any ions. We have things that dissolve in water, but when they dissolve, they don't break apart into charged ions. So good examples are sugar or even alcohols. They mix with water really well. Obviously sugar dissolves in water, but there are no ions formed or no charged particles. So if I'm thinking about this as an electrolyte, if there are no charged particles, I can't conduct an electric current. So in this case, we've got this apparatus. We've got one, but it's broken. You kind of put the prongs in the solution, and there's a light bulb hooked up. If the light bulb doesn't go on, you don't have a lot of ions in your solution. So we could kind of make ourselves a little note. If I'm visualizing this on a particle level, this is a non-electrolyte. The best examples of non-electrolytes really are like sugars, alcohols, things that dissolve in water, but when they do, the particles formed are just neutral molecules. No charges. If I have something like this, the light bulb glows, but it's pretty dim. That's a weak electrolyte. Weak electrolytes form some ions, but not 100%. Most of the molecules are still neutral. The best examples are weak acids and weak bases. And then finally, we've got this solution where the light bulb's glowing brightly. On a particle level, I picture lots of charged ions. So this is my strong electrolyte. My strong electrolyte, and the best example, ionic compounds, strong acids, or strong bases. And we'll test a lot of these solutions in the lab. We'll use a conductivity tester hooked up to the computer, and then we'll kind of prove that, okay, this should be a strong acid. Yep, this conducts more electricity than a weak acid or a weak base. But this particle model is real important when it comes to predicting things like electrical conductivity, strong acid, strong base. What is the tendency of the particle to dissociate and form ions?